little bit. So as I was saying, the various type of experiments you have done till now are mostly based on the GM counter experiment. So what you do in GM counter experiment, basically you have got a source, you don't know the origin, whether it is emitting beta or gamma or whatever. So it is just like that somebody is knocking the door and the door is closed, but you don't know who is out there. So this is the GM counter. It is basically a detector. Okay. So someone is knocking, from the sound itself you are able to understand that someone is there. Who is it? Gamma ray, beta ray or whatever, you do not know that. And using this GM counter, what you did, you put the GM counter in one place. So the first thing what you did was to find the operating point of the detector. Okay. So for that you started biasing the detector, slowly increasing the voltage, and then you measured the count after putting a source close to the GM counter. And as a result you obtained a plateau, and from that plateau, on the linear part of it, you obtained your operating point, and you set the operating point such that if there is a fluctuation in voltage, it doesn't affect your count rate. This is the overall idea. And what are the experiments you did? The first experiment was the statistics. So if you put a source, even without the source, you will get counts. What is the origin? Cosmic gamma rays. Okay. And also the various gamma rays which are present in our surroundings. Say for example the cement. So from cement there is a very nice source. You should remember 40 potassium. Okay, you write it down, 40K. This is an important source of background gamma. Okay, and also try to find the energy it emits, predominant energy. Okay, next, so these are the types of experiments you are doing with GM counter. You can also put a gamma source or you can put a beta source, but you will get some counts. And another type of experiment you have done with GM counter is what you have done. This is the detector and this is the source. You put the source on one flat table and then change the distance from the detector slowly. So after changing the detector, you can observe the change in counts, and from there you can get the solid angle effect, 1 by d square relationship, 1 by r square relationship. You can get flux as a function of distance. So this type of experiments you have done in your first and second semester. Now in this advanced third semester, what we are going to do is, for the first time, we are going to measure the energy. This we have not done anywhere till now. You have no idea about the energy of the particle which is emitting the energy of the receiving photon or beta particles or whatever. Now what about alpha particles? Now in this lab over here, in this lead castle, we have got only two types of sources. One is beta ray and beta particle source, and another is your photon source. Again in photons we have 137 cesium source, which is basically a monoenergetic source, single gamma ray being emitted, most of it predominantly 662 keV. Then there is 60 cobalt, which emits two gamma rays, 1173, 1332 keV. You must remember this. Okay, energies, these are important. Okay, now what about alpha particle? You see, we do not do this in our lab over here. Why? Now in order to detect, in order to measure the energy, or basically what we have to do? We have to do spectrometry. What is spectrometry? Where you measure the energy. So right now I am talking about spectrometry. So we need a spectrometer. Now in case of alpha particle, what is happening is that the moment the alpha particles are emitted from the source, this, if you do the experiment in air, the air, it will immediately interact with the air and it will be absorbed. The range of the alpha particle is very much less in air. So you cannot do the alpha particle counting or spectrometry normally. What you have to do? Of course the answer is there. Remove the air, so that the alpha particles can leave the source and they will be detected in the detector. So how do you remove the air? You use a vacuum chamber. So for doing alpha particle counting or alpha particle spectrometry, we will be using a vacuum chamber. setup. Now, okay, so this is what about alpha particle spectrometry. What about beta particle? In the lab, the type of experiments that we have, what we do is again we are not doing any measurement of energy. So all the beta experiments that we have here, over here and over here, they are basically the same type of experiment that you have done using GM detector. You put the detector and then this time you put an absorber also and try to get an estimation of how much distance the beta particle has traveled by observing the counts. So these are the type of experiments you will be doing in the lab. Now, so we have talked about roughly alpha particle and beta particle. What about gamma rays? So as I was saying previously also, for the first time we want to measure the energy of the emitted radiation. And so let us take an example as gamma rays. So we will be having a isotropic source S which emits gamma rays in all directions. Fine. Now we want to make our life as simple as possible. So what does this mean? Let us have a monoenergetic source. So monoenergetic, isotropic source. Okay. So for this case, we will start with 137 cesium, which predominantly emits the 662 kV gamma ray. Okay. Okay. So this is about source, monoenergetic source. Next one, of course, detector. Now, although I am saying a detector, but basically this is a spectrometer. You must remember, because using this spectrometer, we will be able to measure the energy. Now the type of spectrometer that we will be using in the lab has two parts. The first is a sodium iodide thallium activated inorganic scintillator. What it does is basically after a single 662 kV is absorbed in the detector, it will convert this single gamma energy to more than hundreds and thousands of smaller energy photons. Okay, but do we measure photons in all the experiments that you are doing? No. What are we measuring? We are measuring electrical signal, that means electron flow. Change in the electron flow, this is what we are measuring. So we need another device to convert the low energy photons to electrons. So there is a two-step conversion. You have to remember, this is not like other detectors, spectrometers. Two-step conversion. First, a single high energy gamma ray, it is being converted to a large number of smaller energy photons. Then there is photomultiplier, PMT. And what this does is a single photon energy, when it enters here, of course there is an efficiency, how much it is absorbing. I am not going into technical details. Now, if what it does is single small energy photon, it converts to a large number of say 10,000 electrons or so. So effectively we will having the conversion of this 662 kV to a large number of electrons. Okay, through the two-step process. And as a result, we will having a signal like this, something like this. So this is the electrical signal. And what does this tell me? The area, the entire. If this is the background, then this tells me that this much charge has been collected as a result of the interaction of a gamma ray, which we know from the source of this 662 gamma ray with this detector, and this much charge has been collected. Okay, so this is what we are getting. Fine. Now what are the other types of gamma spectrometers that we can have? Very important one is germanium detector, high purity germanium detectors. There you see they have got very good energy resolution, while this one is very much useful in our lab. This is very robust, this has got good efficiency as well, more than your germanium detector. Although its energy resolution is not that good, but because of being robust nature, it is being generally used in the lab. Another very important reason for not using germanium is that it needs constant supply of liquid nitrogen, which is quite difficult in universities. Okay, so any questions till now? So this is what we have. Now, next step. Next step is regarding this gamma ray. So what are the processes of interaction and thereby absorption? So this is the energy is 662 keV, right? You know gamma ray interactions through which they lose energy in matter predominantly. In this energy range 3, photoelectric effect, Compton scattering and pair production. Now here the energy is how much? 662 keV. So photoelectric effect is there. Compton scattering, it is also there, but no pair production. So only 2. We will be having only 2 processes involved. Okay. So what we will be observing is like this. Suppose this entire energy is absorbed. Let me show you separately. This is the sodium iodide detector. So gamma ray comes, entire energy is absorbed. So what will we observe is a single count over here. Now if large number of such events happen, one after another, say 10,000 times absorptions, what you will see, you will not see a single line. But instead what you will see is a Gaussian type peak, and this is basically, so instead of a single point or line, you are getting this sort of broadened peak. Now this is because of the detector itself. This is known as response function, or the response of the detector itself to this particular radiation. Suppose instead of the sodium iodide detector, I use a germanium detector, then its response will be different. You will observe that compared to this sodium iodide, if I use yet again a germanium detector, what you will see is that it has got a very narrow peak. But remember, the area should be normalized, so the peak will be higher. But we will be working with this only. Acha. Now, so we have talked about this. Now, but when do we observe this? We observe this when there is complete energy absorption. But nobody has told us that there will always be complete energy absorption, right? Who has guaranteed? There can be incomplete energy absorption as well. How? Come on, what happens in Compton scattering? What happens is that, you see, say 662 kV enters, 400 is absorbed, rest 262 escapes. So you will get a peak at 400. Now, if a large number of such events has happened, what you will eventually see is something like this. This is the Compton edge, maximum energy possible due to single Compton scattering, energy loss. And what about in between? This region is due to multiple Compton scattering effects. Say for example, suppose this 662 enters, 400 is absorbed, next another Compton scattering, 100 is absorbed, next escapes. Okay, so these are the type of multiple Compton scattering events. So these are again correspond to partial energy deposition. So you see in this spectrum we have got 2 regions. One is the important one. This is the region of complete energy deposition. Complete energy deposition, and this is incomplete or partial energy deposition. ठीक है सर? So we have got 2 regions. Now of course, which one do you want? We want this one. But it is not possible to just only get this one. This will always be there. Of course there are other effects, many techniques to reduce this part. There are many techniques. Now, so you will be amazed to know that in the experiment that we will be performing, we will get this spectrum. It's very nice demonstration. Okay. Next part. Now what happens in real life experiments? in real nuclear physics experiment. What happens is that here I have just taken a single monoenergetic source, but in accelerator labs or in say fission spectroscopy, what happens is that large number of gamma rays are emitted at a single time from a decaying nucleus, maybe more than 300 or so. And what you have to do is you have to identify, number one, identify the each and every gamma ray, identification. Number two, you have to identify the energy of each gamma ray. Next, identify the intensity of each gamma ray. Okay, now through these three things, what you will be getting is this following. So basically what happens is that this is say an excited state, say E2, this is say E1, and there is a gamma ray decay. Now if we identify and if we do not only energy and intensity measurements but also measurements known as angular distribution, angular correlation, polarization distribution, polarization correlation, we just remember the names. If we do this type of experiments, then what we will get is the spin and parity. Okay, what is the spin? Say 3 by 2 or half or whatever. So basically we will be having information about J and pi of the de-exciting level. Understand? So this is the power of the gamma ray spectroscopy technique. So basically we will be able to get information about the de-exciting level or the structure information of the nucleus. The excited nucleus. So all this is possible just by observing a puny gamma ray. Now the first thing, remember what I said, identification of gamma rays. So if there are 300 gamma rays being emitted at a single time or so, how are you going to identify them? Of course you cannot have a single detector. Now remember Goddess Durga when যখন উনি সংহার করলেন, হ্যাঁ, তখন একটা বা দুটো হাতে করেননি, 10টা হাতে ছিল, ঠিক তো? We will use the same technique over here. We will not use one detector. Instead we will use large number of detectors, and that system is known as a detector array. Now detector arrays can be of gamma detector array type, even charge particle detector arrays are there. Okay, so the aim is to identify each gamma ray in a single detector. So we need a large number of detector arrays. Now write down the name of gamma sphere. You can check it for yourself that it has got more than 100 detectors. So you will be able to identify at least sort of 100 gamma rays at a single time. This is called high granularity of detection. Now what would have happened if all, say I am putting a radioactive source which emits 100 gamma rays here, and all the 100 gamma rays will be detected in the sodium iodide detector. So tell me what will you observe? What you will observe is that if you detect all the 100 gamma rays, sum of the energy, and then the signal that you will get, it will just give you the sum energy. It will not give you idea about the individual energies. It will give you some energy. বুঝতে পারছো? ইন্টিগ্রেশন হয়ে যাবে। আমরা চাইছি ডিফারেন্সিয়াল রেজাল্ট, ইন্ডিপেন্ডেন্ট রেজাল্ট। Remember, as a result of integration, we always lose information about the finite fluctuations. Okay? So if all of them enter here, we will be having a summing effect, integration sort of effect, which we do not want. Now this is what is happening in real life spectroscopy. So you don't have to wonder about it, but this is what the basic philosophy is. Anyway, so this is regarding what happens in a detector and the signal obtained from it. Okay, fine. Next, let me talk about the associated electronics. Now you must be wondering why there is always electronics involved. The thing is that what we want to do is we want to process this signal and understand the but how much charge is being generated as a result of the interaction, and from there we will be getting information about the gamma ray which is interacting with the detector. ठीक तो? Now you see this pulse, this has got two features. A pulse टाके भालो करे देखो. Now there can be positive pulse, there can be negative pulse as well. This is a positive pulse. There are how many parts in it? কতগুলো পার্ট আছে? Number 1, এর একটা পিক আছে, এর একটা উইডথ আছে, but this is not Gaussian. Okay, আমরা এখানে উইডথ নিয়ে চিন্তা করব না. We will not wonder about width. But the pulse height is important. Next, the pulse rising time and the pulse falling time. Okay, now these two informations are very important to us, and we would like to preserve these two information, pulse height information and the rise time information. So pulse height information and pulse rise time information. Why? Reason is that what we should actually measure is the entire area. Okay, কিন্তু এর জন্য আমাদেরকে অনেকক্ষণ অপেক্ষা করতে হবে. This is the time axis. Okay, so এর মানে যখন একটা সিগন্যাল এসে ডিটেক্টরে পড়েছে, so we have to wait for a long time to process the signal if this is very long, and during this time there is a loss. Why? There are other signals entering the detector. So what we want to do is we want to reduce this time. Okay, now this is done in the electronic module which is just after the detector. Okay, so we have got the detector, and after that we have got something called pre-amplifier. Let me first talk about it. Now what does pre-amplifier is that তারপরে হচ্ছে অন্য পার্ট amplifier. Now what pre-amplifier does is it reduces some of the noise associated with the detector, this pulse. Another very important thing is it does impedance matching. Remember maximum power transfer theorem? So power is transferred maximum when the impedances are equal. So what it does, it matches the impedance of detector output to the input of the associated electronics. Okay, this is impedance matching. মনে রাখবে, এটা লিখে রাখো, impedance matching, most important job done by the pre-amplifier. PA, pre-amplifier, that means before amplifier. Okay, so next is amplifier. Now I am talking about this part. So I have to actually measure entire energy, but for that I have to wait a long period of time, but huge time loss. So what I will do instead, I will shorten this time and I will do a pulse shaping. In money, this pulse is actually not Gaussian at all. So in this amplifier unit, I will do a pulse shaping through CR, RC, CR type of. This is a sort of circuit. Through this type of pulse shaping, I will try to get a Gaussian light peak. এবার দেখো কি কি লস হলো. What have we lost? We have lost the entire area, but what have we gained? This significant time সমানে কমে গেল. মানে now we will be able to do a large number of experiments within a given time, large number of measurements. Okay, কিন্তু very important thing, pulse height has been retained. এর মানে এখানে pulse rise time টা retain হয়েছে আর pulse height information retain করেছে. You see, this height is basically proportional to the area of the curve. So instead of measuring the area of the curve, which basically is a measure of the energy, we will be having this pulse height as a number or as a function of the energy carried by the pulse. বুঝতে পারছো? তো আমরা এবার যেটা করব, pulse area spectroscopy না করে আমরা pulse height spectroscopy করব. Pulse height spectroscopy or pulse height distribution. So this is what we will be doing. So this part is done over here in the amplifier. So what amplifier does is it shapes the signal to the Gaussian form, okay, and you see the rise time is retained. খালি trailing time টাকে ছোট করা হয়েছে. Okay, the pulse shaping has been very nicely done, and so দুটো জিনিস করা হয়েছে. One, সিগন্যালটাকে শর্টেন করা হয়েছে. Signal has been shortened. Number two, amplification. What does this mean? Signal has been amplified so that we can now properly analyze it. বুঝতে পারছো? So amplifier দুটো কাজ করেছে, এই সময়টাকে কমিয়েছে, time axis, and this is your amplitude or energy, okay? So এইটাকে বাড়িয়েছে, signal amplitude. So this has been done, okay? Any questions till now? So this is what has been done till now. এর পরের পার্টে আমি আসছি.
টাইম কি বলবো থেকে বাড়িয়েছে?
এই যে আমি এখানে রাইজ টাইমটাকে সমান রেখে যে ফলিং টাইম আছে সেটাকে কমিয়ে দিয়েছি, পালস শেপিং করেছে. সো বেসিক্যালি পালস শেপিং, ঠিক আছে? আর এটা হচ্ছে পালস অ্যাম্প্লিফিকেশন. হ্যাঁ, সো amplifier it does two jobs, pulse amplification and pulse shaping roughly. Okay, now fine, let me erase the stuff. Now comes the most important part. So the most important part of our experiment or the measurement for energy. Remember, we want to measure the energy. ঠিক তো? এবার so if this is an axis like this, so ঠিক আছে? Now this is short, you can say what will you expect? You will be expecting not only full energy peak but also Compton effects. Fine. So you will be expecting a large number of signals of different heights and all that. So this corresponds to the full energy peak. Okay. Now this is your energy height, and this is time. This is what you will see as a function of time. This is what the signals are coming in your circuit. Okay. This corresponds to say 662 kV. কোনো একটা সময় এসছে, আবার এই 662 kV টা এই সময়ও এসছে, ঠিক আছে? ওকে, আর এইগুলো যে আছে এগুলো হচ্ছে কম্পটন স্ক্যাটারিং. দিস ইজ দ্য এফেক্ট অফ কম্পটন স্ক্যাটারিং. ওকে, নাও আমাদেরকে কি করতে হবে? পালস স্পেকট্রাম মেজার করতে হবে, এনার্জি অফ দ্য ফোটন মেজার করতে হবে. কি করে করব? This is done by a unit placed after the amplifier. It is known as discriminator. What does it do? মজাটা দেখো, discriminator কি করে? Basically, এবারে now I will put an electronic circuit and I will put a gate, something like this. This is energy, remember, or basically voltage in the instrument that you will be having. This is basically the voltage. So I will put a voltage window, something like this, a voltage window, and I will say I will now record only the counts which are in between. Now if I do that, কি হবে? এই সব জিনিস হাওয়া হয়ে যাবে, and I will only be able to get information about the signals which are peak within this range. Okay, so this is how your single channel analyzer works. This is a very important discriminator. There are mainly two types of discriminators, other types are also there. So we will talk about the one of the most simplest type. Basically what discriminator does is, if we have a signal say like this, discriminator যেটা হচ্ছে যে ওইখানে একটা threshold সেট করা হয়, threshold. Now after I set a threshold, what will happen? Only the pulses above the threshold, they are being accepted. So this is accepted and they are rejected. So if we have got another pulse at some other time like this will not be accepted, but this will be accepted. So this is the work of a discriminator. Okay, this is how a discriminator works. This will not serve our purpose. What we want to particularly measure the energy. So what we will be doing is the following. We will be considering a single channel analyzer, which is a special type of discriminator. যেখানে instead of one, there are two thresholds. Okay, this is upper level discriminator or upper threshold. This is lower level discriminator or lower threshold. Okay, now what will happen, you see, if we have got a pulse like this, it will not be absorbed. If we have a pulse like this, again this will not be absorbed. Only this one is absorbed. And remember, this is your voltage axis or basically energy axis. Voltage or energy. If I move this energy beam slowly in the spectrum, okay, I will be able to identify my signal pulses and also get the counts. So we have got, after the amplifier, discriminator, then scalar, okay, counter, all that. This is the last part. Okay, so this is what we have. And what is the result? Bolo.
Sir,
Scalar of counter. Okay, so what is the result? End result কি? এর জন্য end result দেখো, end result হচ্ছে আমাদের কাছে we have actually, this is the, say not this one, suppose this is the actual spectrum. Okay, now in order to get this is the counts, number of counts, and this is your voltage or basically energy in kV. This is the actual stuff. Okay, আমরা কি করব, বেসিক্যালি আমরা একটা এনার্জি বিম নিলাম, যার লোয়ার লেভেলটাকে আমি খালি মুভ করব. I will be moving the lower level, but I will be fixing the gap between the lower and the upper level. This is called window. I will be fixing the window. And this mode of operation is known as window mode of operation. লিখে রাখো, window mode of operation of single channel analyzer, SCA, window mode. Okay, now এবার দেখো কি হচ্ছে, এই জিনিসটা এবার যদি আমি আস্তে আস্তে করে মুভ করি, কি হবে, পুরো স্পেকট্রামটা আমি স্ক্যান করতে পারবো. So this is basically how I am scanning the entire spectrum. ভাবো যে এই উইন্ডোটা আমার হাত আছে, ঠিক আছে, look over here. Suppose this window is my hand, the thickness of my hand. So I will start from 0 and slowly and gradually I will do the entire scanning. Okay, so if I do this plot, counts versus voltage or energy, এই যে countsটা পাবো, this will just tell me the information about the spectrum, and I will get entire idea about the partial deposited part and the full energy deposited part. বোঝা গেল? So this is our gamma ray spectroscopy experiment explained in basic terms. বলো.